Okay, now we're going to talk about definition 311, and we'll do the next activity. So definition 311 says, an n by n matrix A is called invertible if there's a matrix B such that A times B is the identity, where In is the n by n identity matrix. The matrix B is called the inverse of A and denoted by A inverse. So then basically we use A inverse is the matrix that undoes A. So equals the identity matrix, and also the other way around equals the identity matrix. The inverse matrix is the matrix that undoes multiplying by A. So in numbers, we would say like 3 inverse is 1/3. It's if I multiply by 1/3, it undoes multiplying by 3. And then we're using the word invertible because some things are invertible. 3 is invertible. 0 is not invertible because there's nothing that undoes multiplying by 0. Now with numbers, 0 is the only uninvertible number. But with matrices, there's lots of matrices that are not invertible. That's why we have to have this definition. Okay, so suppose that now we're moving on to activity 312A. Suppose that A equals this matrix, 3, -2, 1, -1. To find an inverse B, we can write its columns as B equals, column B1, column B2. And so we're requiring that A times B equals the identity matrix. That means that we're requiring that this column and that column are equal to this column and that column. Well, in that case, we're solving like this equation and solving this equation. So to solve these equations to find B1 and B2, then write the matrix B and verify that A times B equals I. Okay, so the next slide, I'm going to do that. So here's A, and here's E1, and then so that becomes, because B1 is going to be my answer to that, so 1, 0, 0, 1, right? So this is the confusing part, because usually we use, this is what we would normally call B, but instead we're calling these guys B. So that means that I'm putting like A, E1 there, and then I do Gauss-Jordan elimination, and I get 1, 1. And then I do A, and I put E2 here, and I do Gauss-Jordan elimination, and I get -2, -3. So then I set B as the matrix who has the solutions to those equations. So then it's 1, 1 because it was E1 had 1, 1. And then the second column is -2, -3. Okay, now let's verify. So 3, -2, 1, -1 times 1, -2, 1, -3. And so multiplying that row times that column, 3 minus 2 is 1. This row times that column, I get a -6 and a +6. They add up to 0. This row times this column, I get 1 minus 1 is 0. And then this row times this column, I get -2. And then a -1 times a -3 is +3. So -2 plus +3 is 1. So yes, I get, they undo, this new matrix B undoes what matrix A does. Okay, now for part B, find the product BA and explain why we know that B is invertible and that B inverse is A. So let's do the opposite order. So my matrix B was 1, -2, 1, -3. 1, -2, 1, -3 times A, which was 3, -2, 1, -1, -2, 1, -1. So multiplying that out, that row times that column is 3 minus 2 is 1. That row times this column is -2 plus 2, 0. This row times this column is 3 minus 3 is 0. This row times that column is -2 plus 3 is 1. So if basically if B undoes what A does, then A undoes what B does. Right? So if A and B, if one of them undoes what the other one does, then they undo each other, as long as they're square matrices. Okay, moving on to part C. What happens when you try to find the inverse of C? So we would have to find -2, 4, 1, -2, and then like augment there. And we'd also have to find -2, 4, 1, -2, and augment there. I think both of them are going to have issues. Let's try this one first. So here I'm going to have the normal thing to do would be to divide this first row by negative. Well, let's just do it. All right, so then first row by -1/2, so you get 1, -1/2, -1/2, 4, -2, 0, and then we annihilate the 4, so 1, -1/2, -1/2, and then so -4 times the first row, add to the second row is 0, -4 times that, add to that is 0, -4 times that, add to that is 2, and so then, of course, you can make that, so 1, -1/2, -1/2, and then 0, 0, and then multiply by 1/2 to there, and so then I have no solution. So when you try to find the inverse of C, you get no solution. So in that case, that means that the matrix C is not invertible, because when you try to find the inverse, you end up with no solution. All right, now let's develop a condition that must be satisfied by an invertible matrix. Suppose that A is an invertible n by n matrix with inverse B. Suppose that B is any n-dimensional vector. Since A times B equals identity, we have A times big B, little b. So B is, remember, little b is, remember, any n-dimensional vector. Then matrix multiplication is associative, so you got AB times B. And then that's just the identity matrix times B. And the identity matrix times anything is just itself. So this says that the equation AX equals B is consistent. So that's consistent. And you could find the vector X. If you have the inverse matrix, you don't have to do Gauss-Jordan elimination. You just have to do multiplication by the inverse. Since we know AX equals B is consistent for any vector B, what does this say about the span of the columns of B? If it's consistent for any vector B, that means the columns, the span of the columns is all of, and we're at n by n matrix, so all of Rn. So because we know that we can find that we can solve for X for any B. So that means that the columns must span the whole space. Since A is a square matrix, what does this say about the pivot positions of A? What is the reduced row echelon form of A? I'm going to kind of answer both questions by doing this one. So that means it's basically 1, 1, 1 to 1, and then all zeros here, all zeros there. Okay. So that means that your pivot positions are along the diagonal. This is the n by n identity matrix. So there's only one type of Gauss-Jordan elimination matrix you get with an invertible matrix. They go, when you do Gauss-Jordan elimination of an invertible matrix, you get the identity matrix. So in this activity, we studied the matrices A is that, C is that, find the reducer echelon form of each, and explain how these forms enable us to conclude. So for A, I just happen to know it's going to be 1, 0, 0, 1. And then for C, we already found it. It was 1, negative 1/2, 0, 0. So notice, like, no pivot. So if your matrix, when you do Gauss-Jordan elimination, doesn't have a pivot in a row, then you're not going to be able to invert the matrix. Okay, that concludes activity 312F.